Erik van Erp giving us the next mini course of the workshop, Hypoelliptic operators and index theory. Thank you very much, Erik. The stage is yours.
All right, thanks. All right, so first of all, I want to thank you guys, to organize this, or actually the two I met. I don't know how many organizers there are. I'm sorry if I insult anyone, but for the invitation. I'm very, very sad that I guess like most people that we can't actually meet in person. I would have very much liked to have the opportunity to meet with a lot of people working in contact geometry, contact topology. But anyway, I hope we can still have an interesting exchange. I've been working on this particular topic, hypoelliptic operators, specifically, first of all, on contact manifolds and their index theory. My origin is in analysis and in index theory, and you know, to me, the contact manifolds were an interesting example because the index theory was started with the work of Atiyah and Singer in the early 60s and was almost exclusively focused on elliptic operators. And so a whole field and machinery has been developed to, you know, understand and extend index theory into all kinds of interesting areas with a focus entirely on elliptic operators. And when I started working on this a while ago, certain hypoelliptic, so I'll talk about what those are. Certain operators that are not elliptic have properties that are very, very similar in many ways to those of elliptic operators. And it turns out that almost all the machinery that has been developed to deal with elliptic operators and their index theory can be adapted. I wouldn't say easily, because it's usually not very easy, but can be adapted and is suitable to deal with hypoelliptic operators in other settings. And contact manifolds are sort of almost the easiest generalization beyond elliptic operators. So that's what I started out doing. And not being a geometer myself, and I don't have any expertise in contact topology. I mean, I read a little bit. I read Geiges's book and whatnot just to have some background material. But I've always hoped that there's some application of all of this in a geometric setting, which would be super interesting. But I've never been able to make a connection. So I really value the opportunity to participate in this workshop. Anyway, that's a little bit my background. So let me just get started. So I'm giving two talks today, since I don't know what people know. So I'm just going to assume I've never heard anybody complain about talks being too easy. So I'm just going to assume that the theory of elliptic operators and hypoelliptic operators is not familiar. So I'm just going to start from scratch. And that's what I'll do today. And then tomorrow I'll talk about index theory, specifically for these operators. So today there's no index theory. I'll just do the analysis. It's actually fairly interesting. And then tomorrow I'll talk about index theory and maybe possibly how this might link to theory of invariance and whatnot for context structures. All right, so we'll start with undergraduate material. These PDEs, anybody take any course in PDEs or differential equations will have seen them. The Laplace's equation, the heat equation, the wave equation. These are the classical elliptic, parabolic, and hyperbolic operators. I think if you know the equation of an ellipse, a parabola, and a hyperbola, you can sort of see why they're called that. It's almost by analogy. And sorry, was there a question? No. And one of these equations, the wave equations, has what are called weak solutions. So, of course, initially, when you apply derivatives, your function has to have at least two derivatives for these equations to make sense. But you can make sense of derivatives of distribution, so it doesn't necessarily have to be a smooth function. And so there's a notion of weak solution of a PDE. And for the wave equation, it's very easy to understand. So For many reasons, you might want to consider a block wave. So it's it's like a 0 or 1 function, and it travels at the speed, at the wave speed, whatever the wave speed is in your equation, right? So that's a valid and interesting solution to that equation, and it's not even, it doesn't have a derivative at, of course, at the points where the function is not continuous, but you can make sense of the differential equation using the theory of distributions. And so weak solutions are very important to consider, because there are many, say, approximation procedures that give you solutions will actually only give you weak solutions. So you definitely want to include those. They're useful for various reasons. However, the other two, so Laplace's equation and the heat equation, the elliptic one and the parabolic one, are what are called hypoelliptic. So I wrote the definition because I feel if you talk about hypoellipticity, you should at least give the definition. But we'll see the definition is not that important. So the full definition says that if you have an equation, P here is a differential operator, so PU equals V. Whenever V is smooth, then the solution U will be smooth. And this is true in any open set. So that's technically what hypoelliptic means. But this is good enough for a first understanding that solutions of the equation, even weak solutions, are automatically smooth, and smooth in the sense of C infinity. So all derivatives exist. Okay, so hypoellipticity is just, you might say, a regularity condition. That, right. Well, also, and so you notice for the heat equation, you can start with a temperature distribution that is not even continuous, right? Some strange distribution of heat, and at any positive time, no matter how small, this will immediately smooth out by the diffusion process. And same with Laplace equation. If you have a boundary condition, you have some voltage on the boundary of a domain that can be very discontinuous. The potential function that's generated in the interior is always C infinity, okay, no matter what the boundary conditions are. So this is what hypoellipticity means. It's solutions are always very, very nice. Okay, now the point is that for index theory and also for spectral theory, if you're studying spectral invariance, hypoellipticity is not really the relevant condition. The relevant condition is ellipticity, but this needs to be generalized. So I'll first review a little bit, again, the theory of elliptic operators, elliptic differential equations, and then we'll see how that generalizes to include certain kinds of hypoelliptic operators. They're elliptic in some general sense, more general sense, and that's a stronger condition than just being hypoelliptic. Okay, so, all right, so for some notation, so I'm going to be writing, all my differential operators are going to be linear. I will forget to say linear because it's a mouthful. So whenever I say operator, I'll just mean a linear differential operator. We start on Rn, that's the easy case. So n variables, and I use the notation you see on the screen. So the A alphas here are constants. I allow complex coefficients here in this theory. And okay, so you take a whole bunch of monomials, you add them up, you get a differential operator. Okay, so I'll pause here for a second. So I try to minimize the texting on memory, but I hope this is not too hard to memorize. So the basic thing is that when I write del j, I mean the ddxj, right? Okay, so the first important tool in PDEs, of course, is Fourier theory. If you take a Fourier transform of a function on Rn, technically actually you get a function on the dual space, but let's not fuss over that. The point is it turns a derivative into multiplication. So if you take an x derivative and you take the Fourier transform of the result, you get the old Fourier transform multiplied with c, and then there's an I there. And this means that if you have a linear differential operator, that also is turned into a multiplication operator. So if V is, say, obtained by applying a differential operator P to U, then the Fourier transform of V is just obtained from the Fourier transform. The polynomial is just exactly the same polynomial that defines the operator, except that you replace every ddx by xi or ixi. And this polynomial is just called the symbol of P. It is, in some sense, has the same information as P. It's just a formal polynomial. The term I'm going to be using mostly is the principal symbol. That's just the highest order part of the symbol. Okay, so you ignore the lower order terms here. Okay, so this is a key tool in this solution and analysis of PDEs. Okay, so what does elliptic technically mean? So an operator, a constant coefficient operator, is called elliptic if its principal symbol is not zero, except, of course, remember the principal symbol is homogeneous, so it's automatically zero if xi is zero, but it can be zero anywhere else. So that's the definition. And back to our, canonical example, the Laplace operator, which is the sum of squares of second order derivatives. If you take the symbol, it's the same as the principal symbol because the highest order, it is all of order 2. You get negative length of xi squared. So this is not zero unless xi is zero. Right, and so this definition generalizes. It's essentially a way of generalizing the properties of the Laplacian. The Laplace operator is sort of the canonical elliptic operator. All right, so then there's a theorem. This is on Rn. This is for constant coefficients. So they have an even stronger property that if you have a weak solution of Pu equals 0, then that solution is automatically real analytic. And I'm not going to go into proof. It's actually fairly easy, but just to indicate a little bit why the symbol not being 0 is a relevant condition. So the reason it's a relevant condition is that you can almost find an inverse for the multiplication by sigma. Right, because the principal part, the highest order part, is invertible. You can take 1 over sigma naught. But of course, for large values of xi, that principal part dominates the lower order terms. And so if the principal part has an inverse, then the whole symbol has an inverse. And so you can find a function, a smooth function, that is almost an inverse for sigma, for the full symbol, say outside of some bounded domain. And then using inverse Fourier transform, and this is part, like I said, it's not that important for my talk, but the fact that the symbol is almost everywhere invertible allows you to prove theorems of this type. So yeah, let me leave it at that. It's, like I said, it's not that important. I just want to point out that invertibility of the symbol is the relevant condition, and it's relevant because of Fourier theory. So, for example, this is a well-known fact. Laplace operator is elliptic, and therefore this implies immediately that harmonic functions are real analytic. Good, it's a well-known fact, but this generalizes it. Okay, so ellipticity means invertible principal symbol, and it's relevant because of Fourier theory. That's the message I want to get across here. All right, what about variable coefficient operators? Because we want to move to manifolds, where it doesn't make any sense to talk about constant coefficient operators. So I use the same notation. You just have to now imagine the coefficients are now functions, smooth functions, instead of numbers. What you do is this: you freeze what is called freeze coefficients at a point. Let's say you have an open subset of Rn. So you just evaluate the coefficients at that point, and now you get a constant coefficient operator. Okay, and the idea is that in a small neighborhood of X, the operator P and the constant coefficient operator are almost the same. They will be very close. Now, hypoellipticity is a local condition. It's a local property of the differential equation. So as it turns out, if you want to prove hypoellipticity of P, it suffices to prove hypoellipticity for these constant coefficient operators. So the definition, one way to define ellipticity is you say that the variable coefficient operator is elliptic if all the constant coefficient operators that you get by freezing coefficients are elliptic. Okay, and so these constant coefficient operators are good approximations of P in a small neighborhood of X. All right, and so on manifolds, then once you know what to do with variable coefficients, you know what to do in manifolds. You just choose coordinates, and then you use the same definition that we use in Rn. So, for example, the Laplace operator on a Romanian manifold. Okay, there's a formal definition which doesn't really matter, but it looks locally in coordinates. It looks like this. There's lower order terms, which are complicated, but they are irrelevant for ellipticity, because ellipticity only depends on the leading term, on the principal symbol. So you don't have to worry about what the lower order terms are. Okay, so what does it mean to freeze coefficients? Well, it just means instead of a function, the GIJs, of course, are is the Romanian metric, or the inverse, I guess. You evaluate it at a certain point, and then now you have a constant coefficient operator. And its symbol is this second order polynomial in the Xi variables. And of course, if you have a Romanian metric, this matrix is strictly positive. So for no matter which value for Xi you plug in, you get something negative, except of course if Xi is 0. And so this makes these constant coefficient operators therefore are elliptic. And therefore the operator on the manifold is elliptic, because all the delta x's, for any x, the operator you get by freezing coefficients is elliptic. So the operator itself is elliptic. A different approach to this, which is maybe a little bit more pragmatic, is to think of the symbol simply as a function of not only of Xi, but also of x. Okay, and then you can all treat it, you can skip over these constant coefficient operators if you like. All right, so that's the definition. And then we get this theorem, right, that any elliptic operator, differential operator on a manifold, is hypoelliptic. So it has this hypoellipticity property. Okay, so I don't want to spend too much time, so it would not be too hard, but I'm not going to go into what happens if you have vector bundles. Many operators that are interesting in geometry don't act on functions, they act on sections in vector bundles. For example, the Hodge-Laplacian, which acts on differential forms, or the Dirac operator of a spin manifold, which acts on spinners. It's easy to extend the definition, so just to say a couple of words about it. You do exactly the same things I discussed. You replace, a derivative by multiplication with Xi, and then your operator will in local coordinates will look like a matrix. So it's a matrix of operators, and so when you replace ddx by Xi, what you get is a matrix valued function. So it's a polynomial of Xi with values in matrices, and those matrices have to be invertible. So instead of not 0, you want them all to be invertible. Right. So the definition extends very easily to this setting. But I think I just wanted to mention that I'm not going to spend any more time on this. So that's what I have to say about elliptic. And then are there any questions so far?
No, looks good for now. Thanks. All
right. So this was mostly meant as a motivation for what comes next. So elliptic operators are hypoelliptic, but the hypoelliptic operators on contact manifolds that are interesting are, of course, not elliptic. Okay, that's why we talk about hypoelliptic. So what I want to do next is to discuss which hypoelliptic operators we actually are actually relevant for contact manifolds, study of contact manifolds. Okay, and this involves what is called the Heisenberg calculus. This is a more complicated machinery, and part of my reason for discussing elliptic operators, even though this is not in here, is that it's a much simpler, much easier to understand than the Heisenberg calculus. And the Heisenberg calculus is sort of a very clever generalization of the theory of ellipticity. So the first thing you do is, instead of using Rn as your model, we're using the Heisenberg group as the model. So here's some formulas. You don't have to memorize the formulas. I assume everybody knows what the Heisenberg group is. If you do anything with contact manifolds, you should know what the Heisenberg group is. So I just wrote it down for, I don't know, legal purposes. Right, so, and partly the fixed notation. So I'll be using x, y, z. X is a vector, y is a vector, and z is a number. Okay, so the other notation I'm going to use a lot are the corresponding vector fields or Lie algebra elements, x1 up to xn, y1 up to yn, and z, where, you know, these are the familiar commutators. All other commutators are 0. Okay, so these are the so for example, z is I think z is the Reeb field, if you think of it as a vector field, and it's central in the Lie algebra. So I'll be thinking of these Lie algebra elements as vector fields on the group. And again, the formulas are not important. I just wrote them down. They're probably familiar. Right. The main reason for me to put them up again is to point out that these vector fields themselves have coefficients. They're not constant coefficient vector fields. So for example, x has a coefficient in front of ddz. Okay. But they're translation invariant. Okay, so that's then the second step. Instead of working with constant coefficient operators like we did in the theory of elliptic operators, those were the model there. Here we're going to work with translation invariant operators on the Heisenberg group. So there's sort of a replacement for, if you like, there are sort of constant coefficient operators depending on how you write the operator. So if you write the operator as a polynomial using the natural vector fields, namely the translation invariant vector fields on the Heisenberg group, then they have constant coefficients. Of course, they're not constant coefficient in the ordinary sense because the vector fields x and y are not constant coefficient vector fields in the ordinary sense, right? But this is the natural replacement for constant coefficient operator. Maybe, you know, abstractly, what we're working with here is the universal enveloping algebra of the Lie algebra. So UG, this red thing on the page here. So that's the relevant. These are the model operators that you analyze first. Okay, so key example. I think there are some talks about sublaplacians. So this is the sublaplacian of the Heisenberg group. Think of the Heisenberg group as in the standard way as a contact manifold. Then this is the sublaplacian, the standard sublaplacian. So this is translation invariant, or if you like, constant coefficient in this suitable sense. Okay, so these are the model operators for this theory. The second thing that's important is to observe that the Lie algebra here, this is a nilpotent group, and it's graded, so in a natural way. You can think of the vector fields x and y just ordinarily as having degree 1, but the Reeb field is given degree 2. This again has it's analogous, you know, in sub-Romanian geometry, the direction, you know, transversal to the contact directions are, you know, they're weighted very differently, right? So, so this is a very natural notion here. What is interesting, I think this is an idea that goes back to probably Eli Stein in the 70s, is that this leads to a different notion of the order of a differential operator. So vector fields are differential operators. They give derivations, and usually they're thought of as differential operators of order 1. But in the Heisenberg calculus, what is done is that the Reed field is treated as if it's a differential operator of order 2. So you just declare that that's an operator of order 2, not of order 1. Okay, the other ones are as usual, but you declare the Reed field to be a differential operator of order 2. And then that affects the order of other operators. So if you, here's just some, I'm going to stick to this example because I wanted one example, so it's not too abstract. If you take the sublaplacian and you add what normally would be a lower order term, so just z, not z squared. If we added z squared, you would, well, if you would get a Laplacian, but I'm just taking z and you put a coefficient. Again, I allow complex numbers. Then the important idea of Stein is that z should be included in the Heisenberg calculus in the highest order part of the operator. It is not considered a lower order term. It's considered a second order term. And so if we next move to what is the principal symbol of this operator, we will have to include this term z, which would not be included if we were testing ellipticity. Okay, so that's a key idea in this theory. The final change, and this is probably the most serious one, is that Fourier theory, which is, very classical subject. If you step back far enough, you will recognize that that is the representation theory of Rn comes into play. Rn is an abelian group, so all the irreducible representations of Rn are one-dimensional, and so you don't really have to think of it as representation theory, but it is representation theory. And so you replace this here with the appropriate analog, which is harmonic analysis. And that's a whole field. So there's nothing special about the Heisenberg group. This works for there's a whole theory about harmonic analysis on nilpotent groups, especially graded nilpotent groups. And the Heisenberg group is in some sense the simplest example. Okay, but this theory extends far beyond contact manifolds, but let's just do one thing at a time. Okay, so just as a reminder, this is all hopefully at least vaguely familiar, the Schrodinger representation known from physics. You represent the Heisenberg group. So every time I write G, I mean the Heisenberg group, not just some arbitrary group. So G is the Heisenberg group in my slides. It's represented by elements of the group are represented by unitary operators on a Hilbert space. The Hilbert space is, in this case, is L2 of Rn, right? Square integrable functions on Rn. And it's determined, it's actually easier to write down the representation of the Lie algebra instead of the group. This is exactly what you see in physics, H bar. Well, in physics, the I factors are different. But H bar ddx is roughly momentum, x is position, and then the commutator is H bar or IH bar. H bar being the Planck constant. Okay, here H bar is just it's just some real number other than 0. So for any value of H bar, you get a representation of the group, and they're not equivalent. So they're all non-equivalent representations. There are some other representations of the Heisenberg group. These are not the only ones, but they're less interesting. So the Heisenberg group has a large abelian quotient, right? If you take the center, which is spanned by Z in the Lie algebra, and you quotient out by the center, you get a map to R2n, the abelian group R2n. So any representation of R2n, and there's lots of them. I mean, again, it's an abelian group, so it's lots of one-dimensional representations. Any of those is also a representation of the Heisenberg group. Okay, I didn't write those down because it turns out they're taken care of in our theory by just considering the Schrodinger representations. Anyway, there are other representations, but these are the interesting ones.
Eric,
okay.
Maybe
yeah.
You're gonna say, but maybe I have a stupid question. So when I think about Fourier theory, I'm thinking like, okay, I'm using like some sort of maybe wave to sample my function, and that's sort of what the Fourier transform does. You sample at different frequencies and in different directions, and you get the transform. So how do you think about this, or how will this show up in a Fourier type thing?
So Fourier, let me go all the way first. This is not very elegant. Here, this thing. Oops. If you see, what is the Fourier transform? This e to the minus ixc. Okay, if you take out the minus there, e to the ixc is, for a fixed value of xc, is exactly a unitary representation of Rn. Right? So what you do here is you have a function on the group, u is a function on the group, and this is basically what it looks like in all the different representations. So you can think of this as a group algebra. You have an element in the group algebra. It's represented by a scalar in each. Yeah. So and then ddx. So that's this is essentially what we're doing here. So a constant coefficient operator is an element in the universal enveloping Lie algebra of Rn, which is also Rn. Okay, and the symbol sigma is just its representation. If you take the irreducible representation corresponding to the number xc in the dual vector space. So sigma xc for a certain value of xc, sigma of xc is in some sense, and quite literally, a representation of p, which is an element in the universal enveloping algebra.
I see.
So this is literally representation theory. Of course, nobody ever thinks of it that way because it doesn't help and it's just highbrow. But that's the analogy. And it's not an analogy, it's literally the same. That's kind of what I'm trying to say.
All right, thanks.
Sure. And then where was I? On this. We were here, right? I think. Yeah. Okay. Yeah. So yeah. So the reason it looks so different here is that so now instead of a number for each h bar, you don't get a number, you get an operator. Okay, so you don't get a function of h bar or something like that. You get actual, for each value of h bar, you get an operator. So it's a much more, I don't know, serious object than what you get in Fourier theory. But it's completely analogous. That's what I'm trying to say. Okay. And of course, these just as before, these representations of the Lie algebra extend in an obvious way to the universal enveloping algebra of the Lie algebra, and therefore to translation invariant differential operators, which is the same thing. Okay. All right. So then here's what invertible principal symbol means, and it's what I'm trying to emphasize is that it's literally the same thing, although it looks very different. You want this. You take the highest order part of your operator. It's translation invariant. You represent it in one of the Schrodinger representations for some value of h bar, and then it has to be invertible. Now, let me unmask the remark. It's only required to be invertible for h bar equals +1 and -1, but that's just for convenience because the p0, this highest order part, is homogeneous of some order. And there's a certain kind of symmetry in the representation theory that if it's going to be invertible at +1, it's going to be invertible for all positive values of h bar. If it's invertible at h bar is -1, it will be automatically invertible for all negative values of h bar. And then lastly, if it's invertible for all values of h bar, it's also invertible in all the scalar representations of the Heisenberg group. So that's why you don't have to mention those. Okay. So the real underlying condition is that you want this. So you take the dual of G, the unitary dual, G hat, which you then write down, which contains irreducible representations. And this highest order part of the operator has to be invertible in all of those representations, except for the trivial. The trivial representation is the representation that sends every group element to the identity. Okay, there the thing is never going to be invertible. It's always 0, just as in the case of Fourier theory. All right. So yeah, thanks for asking that, because it's hard to see when you first see this that it's really exactly the same thing that we used in the theory of elliptic operators. It's just you've replaced the abelian group Rn with a nilpotent group. And this can be any nilpotent group, any graded nilpotent group. It doesn't have to be the Heisenberg group. So the same exact theory works on other nilpotent groups. And Rn is, of course, a nilpotent group. but there's other, see, there are things like you can take Rn with a grading. So you can make a certain part of Rn of degree 2 and another. Then what you're modeling is foliation theory, where you know, the leaves are given order 1 and the transverse part is order 2. And then you get, for example, a theory that explains why the heat operator is hypoelliptic. Okay. So in this setting,
yeah, ask. So you're saying that H bar takes the role of Xi.
Exactly. Yeah. Yeah. Yes.
And,
yes.
And you said that there were other representations of this Heisenberg group.
Yes.
But you don't, because the exponential EI Xi X are all representations, no? Or is it? So for Fourier, you use all representations, but here you just restrict to some, or?
Well, okay, that's a good question. Let me go back to the ellipticity condition here. So first, remember that the principal part of a principal symbol is a homogeneous polynomial. So if the symbol is not 0, say, for all values of Xi where the length of Xi is equal to 1, so in other words on the unit sphere, then of course it's invertible everywhere except at 0. So that's the first restriction I'm making. I'm only considering X's of length 1. That's why I can take H bar to be +1 and -1. I don't have to take the other values. It's similar there for similar reasons. So so back to this one. Right, so that explains very vaguely, but what I'm saying is true, that if you take the other values of H bar, it will also be invertible, if it's invertible at these two values. Now, there are also scalar representations, one-dimensional representations, and that's a little bit harder to explain quickly. What's the best way to see that? Yeah, let me not, I can only give a very vague reason, but it's a theorem that if all the representations for all values of H bar are invertible, except for 0, then all the scalar representations will also be invertible, except for the trivial one again. That's the one that's at the origin.
And to understand the analogy, so this is like the theory for constant coefficients.
Yeah. Yeah.
Okay.
Exactly. Yeah. Exactly. Yeah. Exactly. Yeah. You know, the best way to put it is, I can't point at anything, unfortunately, but the UG, what I call here UG, the universal enveloping algebra of the Lie algebra, those are the elements you can represent. And if you think of them as differential operators on the group, this condition implies hypoellipticity for such operators.
Okay, thank you.
Yeah.
Thanks.
Can you maybe comment on this word nilpotent?
Sorry?
So you said like everything works for nilpotent groups.
Nilpotent,
so,
yeah.
Can you comment on that, or is that a whole story?
You mean why it works, or?
Yeah, why do you need this condition?
Why do you need this condition? Well, the representation theory for nilpotent groups is a subject in of itself, right? It's very different, say, from the representation theory of semi-simple groups. So nilpotent groups are close enough to abelian groups that you can, if you look at the proof of the theorem I wrote down here, you'll see that it actually relies very heavily on ordinary Fourier theory. So the reason, I think, the way I understand it, the reason it works for nilpotent groups is because they're not too different from abelian groups. So you can sort of push some of the technology that works for elliptic operators. It's quite it's not easy, but it can be. You can use ordinary Fourier theory to prove these things. Yeah, I hope that. I mean, it's a vague answer again, but.
Oh, that helps. Thanks.
Yeah, you have this picture where I don't know if you know Kirchhoff theory, but let me not go into that. That's kind of too much of a detour. The representation theory of a nilpotent group is closely related to the dual space of the Lie algebra G star, right? And then you on G star, and that's Kirchhoff theory, and that plays an important role in all of this. And it only works for nilpotent groups. Yeah. Anyway, the analogy is kind of striking, and I guess what I was saying at the beginning, it is remarkable that it was to me anyway that every time you look at some extension or development in index theory over the last 60 years that was all developed for elliptic operators, almost all of it applies to these types of operators. Because the analogy is so close. I mean, it's not really an analogy. It's literally the same thing if you understand it at the appropriate level of abstraction. And so a lot, yeah, all of that machinery can be applied, adapted, I should say, to these operators. Okay, so let's do an example, see a little bit how this works. That makes it maybe a little bit more concrete. So the sublaplacian again. So G is, of course, a contact manifold, the standard contact manifold, I guess. This is the standard sublaplacian on the Heisenberg group. And this is an example of an elliptic operator, Heisenberg elliptic operator. So here's how this goes. You take the Schrodinger representations with h bar plus or minus 1. And so x is represented by ddx, y by x, and then there's some factors of I that I forget, can never remember. I think y becomes ix, and so you square it becomes plus x squared. And h bar squared is 1 in each case. And so what you get here is a harmonic oscillator. Back to your early question, if h bar is not plus or minus 1, you get an h bar squared in front of ddx squared. And so then you have to do a little bit of change of variables to see that those things are also invertible. So the harmonic oscillator is very well known. We know the spectrum of the harmonic oscillator starts at n, and is positive, of course. And so this operator has a bounded inverse. Okay, and so that makes the sublaplacian elliptic in this particular calculus. The scalar representations are much easier. So in this, if I had done that, I didn't prepare that, but if you take the scalar representations of the sublaplacian, you would get something like c squared plus eta squared. Okay, so that is a function. In this case, it's a number, and those numbers are never 0 except that c and eta are 0. So I try to stay within my time limits, but the other representations are actually really easy to deal with. So there's nothing. I'm not hiding them because they're complicated. I'm hiding them because they're less interesting. Okay, so this is how it works for this operator, and then here's a slightly modified example. So we add a z term. So again, gamma here is some complex number. Then now this is one of the strange features of the Heisenberg calculus. Here's the condition for this operator to be elliptic in this setting. And you see it's very odd looking. There's some very specific set of values. Of course, you can sort of see here this has something to do with the spectrum of the harmonic oscillator. If gamma is any other number than the numbers listed here, then you have a Heisenberg elliptic and therefore hypoelliptic operator. But if you pick one of these values, it's no longer a hypoelliptic operator. And this is sort of a quantum effect which occurs because the symbol, the values of the symbol are operators. It's an operator valued symbol. And so you get this non-commutative effect appearing here, which you don't see in the theory of elliptic operators. So just to go through it, Z, as I said earlier, is to be considered as an order 2 differential operator. So the highest order part of P naught, is the same thing as P. To include the Z, it's important here. And then you look at the representations, the Schrodinger representations. Okay, so we already saw that the sublaplacian is represented by the harmonic oscillator on L2 of Rn. And Z, which is the central element, is represented by a scalar, I h bar. And so you get, for +1 and -1, you get these two operators on L2 of Rn. And so these both of these have to be invertible. And those are two separate conditions. So the first one has a bounded inverse, of course, if -I times gamma is not in the spectrum of Q, and the other one is the other way around, is a different sign. And so then if you go back and look at the spectrum of Q, you get exactly the condition in red at the top of the page. Right, and so here this is an example where you see that h bar +1 and h bar -1 really are independent. These are two independent conditions. If you were to take other values of h bar, again, you would have to do some change of variables to see that they reduce to these two cases. Okay, so this is a very odd looking example. If you use the elliptic operators, which this is a different audience, but I talk a lot to people in index theory, this looks very strange for people used to working with elliptic operators. It also very clearly indicates that the hypoellipticity of this operator is not a function just of the highest order part in the ordinary sense. It's in fact the lower order term, what normally would be considered a term of order 1, the Reed field. That's the determining coefficient here. So it's this idea that this operator Z has to be treated as being on equal footing with the sublaplacian is obviously necessary here.
Can I ask something?
Sure, of course.
Is this fact that we consider the Z also as the same order of the operator also related to the fact that the dilation in the Heisenberg algebra are not homogeneous of degree 1, but they go like 1, 1, 2?
Exactly. This is exactly yeah.
So in general, if we consider general nilpotent classes, we would have to basically look at that, and we could say which is of higher, which is what order.
Exactly. So the theory, yeah, exactly. That's exactly the right idea. So whenever you have a dilation on a, so the nilpotent group has to be graded. You get a dilation with different, weights, if you like, in different directions. Those weights determine the order of the vector fields in those directions.
Thanks.
And the theory is exact. So everything I'm saying here about the Heisenberg group works for those groups exactly the same way. Yeah. And like I said, it doesn't even have to be nilpotent. It can be graded abelian, for example. So that's how the theory applies to foliations. So you can arbitrarily declare certain directions to be of order 2 and other directions of order 1, or whatever you want. Of course, the thing is you have to find interesting examples where this actually is useful, but there's a lot of freedom here. This works in very great generality. So, for example, you can have manifolds, what are they called? Heisenberg manifolds that are, they're contact manifolds in some open set and maybe foliations somewhere else. I think confoliations or whatever these things are called of Thurston. All this works in that setting. It's very general. Yeah.
Thanks.
Sure. All right. Now, as before, the constant coefficient operators or translation invariant operators are the model. I call it the model. Like that's the model problem where you use representation theory. Of course, then the question is, what about differential operators on manifolds? It doesn't make any sense to talk about, translation invariant or whatever. So you want to now address what happens with variable coefficients, just as we did for ellipticity. And the solution is also, again, the same. The same when understood in the appropriate manner. So you express whatever differential operator you have as a polynomial not in the coordinate vector fields, which is what you normally would do. So you don't use ddx1 up to ddxn to write the operator. You just use the vector fields x, y, z to write the operator, and then it becomes a polynomial. Of course, it will be a polynomial now with variable coefficients, not with constant coefficients. So it takes a little bit getting used to, but it's, you know, you just use some different set of vector fields than the coordinate vector fields. Of course, they don't commute, but that's not a problem. Then you freeze coefficients at a point of the group. So XYZ, like I said, is a point in the Heisenberg group. And then you, just as before, we have not a constant coefficient, we have a translation invariant operator. Okay, and so the operator, any differential operator on the Heisenberg group is Heisenberg elliptic if all these translation invariant operators that you get by freezing coefficients are Heisenberg elliptic. Okay, so that is, like, again, exactly the same definition that I used for ellipticity. And it works for the same reason. These translation invariant operators are models that are easy to analyze relatively, and they're very good approximations to the operator, to the variable coefficient operator, as long as you stay close to the point XYZ. And that hypoellipticity, again, is a local property, so this allows you to prove hypoellipticity. Okay, so here an example. Now imagine this is the same example I had before, but instead of gamma being a number, I allow it to be a function. So I have a variable coefficient. This is still in the Heisenberg group. Okay, now, okay, so it's fairly straightforward. You freeze the coefficient, what do you get? You get exactly the same thing, but gamma is just given its value at that point. So now it's a constant coefficient operator or translation invariant operator. And we know when this is Heisenberg elliptic, we just tested it out. Okay, so P is Heisenberg elliptic if all these constant coefficient guys are Heisenberg elliptic, which is exactly if gamma is a function, complex value function, which never hits one of these forbidden values. And what you see here is that gamma actually now has some interesting topology, because if you take C as a plane, the complex plane, and you take out a whole bunch of points, this is no longer contractible, right? This is non-trivial homotopy. So now, of course, G is not interesting because G is contractible. So, but once you have manifolds, there can be interesting topology in the coefficient gamma because of these forbidden values. That will play a role tomorrow. Okay, there's a special case of this. Of course, if gamma is real valued, then this is automatically a Heisenberg elliptic operator. That's something that was known. There's an older theory by Hermander. We call it sums of squares operator. So if gamma is real valued, then this is hypoelliptic by an older theory. But this is only a remark that's useful if you're familiar with this example of Hermander. Otherwise, it's really not that important. But what this shows is that allowing complex coefficients introduces some interesting topology that it really isn't there if you only allow real coefficients. Okay. Okay, so this was still in the Heisenberg group. Now, of course, passing to contact manifolds is fairly straightforward. Contact manifold is locally a Heisenberg group. Okay, I think Darboux theorem is a theorem in symplectic geometry, but I think this same thing for contact manifolds is also called Darboux theorem. I'm not sure. Like I said,
I know it also in contact as Darboux theorem, but maybe.
Yes.
Sometimes we say Darboux pfaff, but I define contact manifold like this. So this theorem is a definition of contact manifold.
Okay, good. All right. So yeah, so I wasn't 100% sure if this is also referred to as Darboux theorem, but I'm glad to hear it is. Anyway, so okay, so again, all of this is local. So if you can do it locally on the Heisenberg group, you can do it on contact manifold. So the same thing. Say you have a contact manifold, contact form. It has a, well, to make a sublaplacian, you have to make some choices. You need a metric in H, or guess a sub-Romanian metric. And then Z is just a Reeb field of the contact manifold, and you can do the same thing, right? So you can write this this operator, differential operator of order 2, and you get the exact same condition that you got on a group. The coefficient gamma has to avoid these forbidden values. And then it will be a Heisenberg elliptic operator. Okay, so this is a crash course in Heisenberg calculus. There's a lot more to say about it, obviously, but I wanted to stress the analogy with elliptic theory. I hope that came across. Okay, and then there's the theorem again that every Heisenberg elliptic operator, differential operator, is hypoelliptic. Right, so it has this nice regularity property. So I'm almost done. So I think the analysis that may be relevant for this conference, there's on the one hand spectral theory, say the spectrum of the sublaplacian plays a role. I'll be talking tomorrow a little bit about index theory. But we say, you know, index theory of hypoelliptic operators, that is just to not have too many words to say. What I wanted to say though is that hypoellipticity, while it's a nice property, is not really the relevant property. The relevant property is this having an invertible principal symbol, but just in a suitable calculus, not necessarily in the ordinary calculus. So I have colleagues, I don't like this, who start using the word elliptic for, you know, so this operator here that we had here, this red operator delta H plus gamma Z, and they just call this an elliptic operator because the analogy is so strong. They feel that this should just be called elliptic, but I don't know. I think this is very confusing because the word elliptic is so well established, has a very well-defined meaning to, you know, most people who don't work on nilpotent groups. So I think it's somewhat of a bad idea. On the other hand, so just to accommodate a little bit, I put elliptic here in quotation marks. So when I say elliptic in the talks today and tomorrow, elliptic in quotation marks means, say, Heisenberg elliptic, so with an invertible symbol in the sense that I just explained. There is no good word for these operators, so we usually refer to them as hypoelliptic operators. They are hypoelliptic, but it's a stronger condition than just being hypoelliptic. And it has much better properties than some arbitrary hypoelliptic operator. And the second remark, we've already, because of some of the questions, I already touched on this. So the calculus for contact manifolds is the one I just discussed using the Heisenberg group. But then, as was already asked earlier, you can use other nilpotent groups as long as they have a dilation, they're graded. And so this model, not just the groups, but also manifolds that are modeled by such groups. So just some random examples, foliations. This will lead to operators that are a little bit like the heat operator. You can use something, I don't know if these things are of any use, but quaternionic contact manifolds based on the quaternionic Heisenberg group. So they have a distribution of codimension 3, any graded nilpotent group. So you can go crazy here. There's a vast area of hypoelliptic operators, and the theory is goes through for all of those settings.
Eric, there is a question in the chat. If gamma is equal to I times n plus 2, is it clear that the operator is not hypoelliptic?
So I know the answer for sure on if you have a constant coefficient and you're on the Heisenberg group. So I know for a fact that that's a good question, actually. I'm not 100% sure. So here we're on the group, and here, so I say it's Heisenberg elliptic if and only if, so that's just a definition. But this is hypoelliptic if and only if gamma is not in those, not a value, one of those values. So for the Heisenberg group, we have a constant coefficient operator. The answer is yes. So hypoelliptic if and only if gamma is not one of those values. So if it does, if you make it equal to in, it will not be hypoelliptic. So I suspect that the same is true for a variable coefficient, but I'm not off the top of my head. I don't know any theorem that says that. So I'm not going to claim to know something I don't know. But I would be surprised if it wasn't the case.
Okay. Thanks a lot.
So I think, I don't know how much time I used. 11:30.
We are basically out of time, but
I'm
we
sorry,
have also a number of questions, so I won't be so hard on myself. Thanks a lot. So let me thank you. It was a very nice